Alright, this video is going to be about similar figures with a focus on similar triangles. So what are similar figures? Well, those are shapes that have the same shape but potentially different sizes. One way to create similar figures is by doing a transformation called a dilation, which is increasing or decreasing the size of a figure but keeping the shape the same. So in terms of measurements, what does that mean? This means that all of the corresponding angles are congruent, and it also means that all of the corresponding sides are proportional. So we'll look at some examples of what that means. So in these figures here, if they are similar, corresponding angles should be congruent. So for example, this angle should be congruent to this angle. This angle should be congruent to this angle, and so on. Proportional means that there's a constant ratio between the side lengths of one figure and the side lengths of another. So for example, I can multiply any side length in this figure by 2 to get the side length in this figure. Right, 6 times 2 gives me 12, 5 times 2 gives me 10, 1 times 2 is 2, and 4 times 2 is 8. So we usually demonstrate proportionality by writing out proportions, writing out sets of ratios or fractions that are equal. So there's a couple different ways that I can show proportionality. I could set up a proportion between corresponding sides from the two different figures. So for example, I could say orange from the small over orange of the big is equal to the red side in the small figure over the red side in the big figure. And then I would want to make sure that this statement is actually true. I can see that 6 over 12 simplifies to a half, and 4 over 8 simplifies to 1/2 as well. So yes, this is true. And I would need to check that all of the sides are proportional. Just because 2 of the sides are doesn't mean that the rest of them are. Another way that I could set up the proportion is by setting up fractions between sides in the same figure. So for example, I could set up purple over green in the small figure is equal to purple over green in the big figure. And then again, I would want to make sure that those fractions are actually equal. I know that 2/10 simplifies to 1/5, so yes, these are equal. So that's how we can show proportionality between the sides of two figures, is by showing that the ratios of their sides are equal. So either setting up proportions where we have fractions of corresponding sides from different figures, or setting up proportions where we have sides from the same figure corresponding to sides from another figure. One thing to note if you're not sure which side corresponds to which in similar figures is that the smallest sides will match up with the smallest sides. So for example, in this figure, the purple one is the smallest one, and purple is going to be the smallest in this figure as well. The next biggest is the red one, and the next biggest in this figure is also the red one. Next is green, the next biggest is also green, and the very biggest side is the orange side, and that's true in this figure as well. So if you're having trouble figuring out which side corresponds to which, try to match up the smallest side with the smallest side, biggest side with the biggest side, and so on. So we said proportional means that there is a constant ratio between the side lengths of the two figures, and we call that constant ratio the scale factor. So the scale factor is basically what you multiply the sides of one figure by to get the sides of the other figure. So for example, if I was transforming from the small figure to the big figure, my scale factor would be 2 because I multiply the sides of the small one by 2 to get the sides of the big one. So if your scale factor is a number greater than 1, then your new figure will be bigger. Than your original figure. But we don't always have to make figures bigger, we can also make them smaller. So for example, if I started with the big figure and I wanted to transform it into the similar smaller figure, then my scale factor would be 1/2, because if I multiply these sides by 1/2, I get these sides. So if you have a scale factor that is less than 1, then that will create a new figure that is smaller. And there's one, and that will create a new figure that is the same size. So in essence, this will create congruent figures. So congruent figures are a special type of similar figures. All congruent figures are similar because they have proportional sides with a scale factor of 1. But as we can see, not all similar figures are congruent. For example, these figures are similar, but they are not the exact same size. In this example, it's pretty easy to find the scale factor in our heads, but it's not always going to be such nice numbers. So in order to find the scale factor, all you have to do is divide the sides of one figure by the sides of another. So for example, if I wasn't sure what the scale factor was here, I could do 6 divided by 12, and that gives me 1/2, and that's my scale factor. So you want to do the side of the new shape divided by the side of the old shape. So if I was going in the other direction, from the small to the big, and I wanted to figure out my scale factor, I could do 8 divided by 4, and that would give me my scale factor of 2. So to find the scale factor, just divide the new side by the old side. So sometimes we can use similar figures to do some solving. Like in this example here, we're going to solve for this missing side length. Before we do that, I want to point out this notation at the top. This is called a similarity statement. So a similarity statement is just a collection of the letters of each triangle with this squiggle in the middle to mean is similar to. So we would read this statement by saying triangle ABC is similar to triangle DEF. The reason similarity statements are helpful is because they show you which angles correspond to which in the different triangles, based on the positions of the letters. So the first letter in this triangle is going to correspond to the first letter in this triangle. So angles A and D are corresponding. The second letter will correspond to the second letter, so angles B and E are corresponding, and we can see that because they are congruent. And then angles C and F are corresponding. And we can apply that to side lengths as well. So for example, here I've got side BC, that's going between the second and third letters. So I know that that's going to correspond to the side between the second and third letters in this statement, which is EF. So you always want to check your similarity statement to make sure you know which angles correspond to which, because sometimes a diagram will be flipped around, reflected, rotated, and it will be a little hard to tell which angle goes with which. All right, so let's use the properties of similar triangles to solve for the missing side length. Since we're told that these triangles are similar, we know that the sides are proportional. So there's a couple different ways I can set up my proportion here. I can say 30 over 36 is equal to the same ratio of corresponding sides in the other triangle. So we said BC corresponds to EF, so 15, and BA corresponds to ED, so X. So that's one way I could set up the ratio. Another way is that I could do 30 over 15, and then set that equal to 36 over X. So either of these proportions totally works. You'll get the same answer either way. We'll just go with the first one. Now you could probably solve this without doing cross multiplication, but I'm going to show that method just as an example. So when you have a proportion, you can solve using cross multiplication, which means you multiply the numbers that are diagonally across from each other, and then set those products equal. So I would have 36 times 15 is equal to 30 times x. 36 times 15 is 540, and we've got 30x. And to solve that equation, we're just going to divide both sides by 30. And we'll wind up with 18 equals x. So in using the properties of similar triangles to set up a proportion, I'm able to solve for the missing side length of that. The last thing we'll talk about is the 3 theorems for proving that triangles are similar. So we said that similar triangles have congruent angles and proportional sides, but we don't need to prove that every single angle is congruent and every single side is proportional. There's 3 sets of minimum information that will show that 2 triangles are similar. The first one is called angle-angle. That says that if 2 triangles have 2 pairs of congruent angles, then the triangles are similar. So that might look like this. We can see those triangles have 2 pairs of congruent angles, so that's enough to know that those triangles are similar. The second one is side angle side. If we know that 2 triangles have 2 pairs of proportional sides and a congruent angle between those sides, then that's enough to know that they are similar. So this might look like having a congruent angle and having proportional sides next to that angle. So I'm going to pick a scale factor of 4. I'm going to say this side is 2 and this one is 5. 2 times 4 is 8. 5 times 4 is 20. So you can see that the sides are proportional. There's a constant scale factor of 4. And there's a congruent angle sandwiched in between those sides. It's important that the angle is in between the proportional sides. So if it was this angle that was congruent, that would not be side angle side. That is not enough information to know that the triangles are similar. It has to be the angle that is sandwiched in between those proportional sides. The last theorem to know that triangles are similar is side, side, side. So if we know that all 3 sides are proportional, then that's enough information to know that the triangles are similar. So for example, if these sides are 3, 4, and 5, and my scale factor is 1.5, this would be 4.5, 6, and 7.5. So if I know that all 3 pairs of sides are proportional, then that's also enough information to know that the triangles are similar by this side, side, side similarity theorem. And those are the basics about similar figures and similar triangles.